recording. Okay, so for the last part of the winter school now, we're going to look into interfacial axis calculation and mapping. This is something that's maybe not done as often as it should be. I think I've given the motivation already in the field of vibration physics part, because if you go to interfaces, especially grain boundaries, the concentration is not very often a particularly good measure of the of what's happening at the grain boundary. So the concentration, the maximum concentration, can be very much influenced by the orientation of the interface in our atom probe data set. Yeah, so if we're measuring along, or if we're measuring across, or any angle in between. Yeah, so we need to have a bit more robust value, and that's been around in atom probe for a very, very, very very long time. And the first works in that regard were, oh, Microsoft Bing, why? I don't want Microsoft Bing, please don't. Were in the early 80s, but the type of measurement that most people do these days actually traces back to this paper by from David Seidman's lab at Northwestern. It's kind of funny because it's David Seidman is still active, and this paper is from '93, and David Seidman was not a young man in '93. Yeah. And essentially the way it works is that we use cumulative curves. So you just imagine you have an interface, a grain boundary, somewhere in your data set. Yeah. And then what you're doing is you're plotting the cumulative number of atoms of whatever species interests you versus the number of all atoms. Yeah? And if you do that, you will get a sort of constant sloping line on either side, which represent concentration in the first on one side of the interface and concentration on the other side, and in the middle you're going to have a higher slope than on either side. And if you go and you extrapolate those concentrations into the plane of the interface, which in our case we're actually going to know. Here it's sort of an estimate of where that could be. We have outlined our interface, so we can actually know where the interface is. And this way, so this is some data from 1D atom probe, so you can see, okay, it wasn't all that easy to do those estimates back in those days, but we're going to have it much easier because we've created an automated way for this to pop up for you. So it's going to be relatively easy to do that analysis once you have outlined the interface. You could use any kind of interface again. You could use an isosurface if you, for example, have a precipitate outlining an interface, or it's a phase boundary maybe that can do that. This is what we're going to use here. And so we're going to start with a very simple example. Maybe before that, let's just dive into some subtleties of thermodynamics here that we need to understand, mostly because some people will throw in some pretty sophisticated thermodynamics language for stuff that is actually super simple, especially when it comes to experiments. So what we're looking at now is we're going to have some interface made up by a piecewise linear approximation, just like we had it in all sessions so far, and we are going to have some atoms around here and maybe a few more somewhere further out here. Maybe we have some preferential retention, so we might have a few more on one side than on the other side. but that's not really the question. And so the question is, what is the interfacial axis? And the interfacial axis gamma, is the number of individual atoms that are there in excess per unit area, also per area. So we're going to need the area of the interface. That's why we're going to do the modeling. And we're going to need the number of excess atoms. That's why we're going to do this whole ladder diagram, cumulative curve thing. So the difficulty with that is now people very often talk about things like Gibson interfacial axis and Guggenheim interfacial axis. Very often you will hear Gibbsian interfacial axis, and people, because the good name of Willard Gibbs is intimately connected with thermodynamics, will assume that the interfacial axis is a thermodynamic value, and it is not. The Gibbsian interfacial axis is not a thermodynamic value, and the reason why it's not a thermodynamic value is because the Gibbsian interfacial axis is determined at the Gibbsian plane. So just imagine we have another species that it defines the interface, maybe a gray species, where we have a lot of atoms here and a few here, and we might have a concentration profile, proximity histogram, concentration profile, whatever. So what we're not taking into account is actually curvature. There are some corrections from a certain Mr. Faulkner from the 80s who's taking care of what happens if there's curvature. We're not going to take care of that. So if we plot concentration versus distance, concentration versus distance, distance d, for our gray species here, then assuming we are having our surface normals this way, on a positive surface normal side, we're going to have more. So it's going to look something like this. And the question is now, where is the interface? Which is very much related to our isosurface problem. And the interface, the Gibbsian interface, is actually at a plane here, such that those two areas are actually the same. So this equals this. So does anyone have an idea why this can never be a thermodynamic value because of that? No ideas? Everyone zoned out already? No thermodynamic specialists? Well, because we have a concentration for this, oh, no, wrong. Go back to gray. So let's call this atom A, and this is atom type B. And so what we have is we have defined our interface based on atom type A, which means that the location of interface depends on the choice of reference, species, which means it's not independent, and a thermodynamic value must always be independent of the frame of reference. In this case, it's not independent. So our Gibbsian interfacial axis is always the interfacial axis of a species I, with respect to a species J. And in our case, that's A. So we would measure a gamma. So we would measure a gamma of B with respect to a gamma of B with respect to A. And this is a choice and thus not a thermodynamic value. On top of that is the whole business of, just imagine that being a grain boundary. If it's a grain boundary, a concentration profile would look like this. Where would you find a point where this is true in a grain boundary? Where the sum of these two is 0. There is no such plane in a there is no such plane in the grain boundary. It doesn't exist. Yeah. So a grain boundary is not a Gibbsian interface to begin with. Of course, a grain boundary is an interface, but it's not a Gibbsian interface. Yeah? And this is the reason why Gibbsian interfacial access is not a thermodynamic value. There's a couple of other justifications of which pairs of things can constitute thermodynamic values, but we're not going to discuss it in depth. But the important thing, this is not a thermodynamic value. There's actually a different type of thermodynamic value, which is called the Guggenheim interfacial access, and that is a thermodynamic value. And a Guggenheim interfacial access assumes the existence of an interface phase. So let me just draw that. So this is Gibbs. This is a grain boundary. No. This is a grain boundary. This is, by the way, not news. Mr. Guggenheim was already found out in the 30s that the Gibbs interfacial access is not a thermodynamic value. Yeah. So I've been accused of smearing the good name of Mr. Gibbs before, but you know this is settled. Yeah? This is settled. This is just the way it is. Okay, so in the Guggenheim view, what we can do is essentially have the concentration of our species B that we're actually looking at, yeah, which might have some excess here, yeah, and it doesn't need to be concentrations on both sides. Yeah. And in this case, it is just said that we have a domain, an interface domain, and we have a non-interface domain. So we have a bulk domain and an interface domain. And what we calculate is actually the amount of excess material in the interface domain if those boundaries are far enough to not be influenced by the interface. Of course, from a practical point of view, you could now also argue it kind of depends on where you put those. But that's a discussion for another day. So how does that actually influence us as users? Does it really? Because if we look at the Gibbs definition, well, the question is, where do I put the interface? Yeah? And the question for us is, I mean, you can try and put the interface 3 nanometers further out in one direction or in the other direction and see if you're going to get much of a difference. And I can guarantee you the difference is going to be rather marginal. So from an experimental point of view, for us, the difference between Guggenheim, between Gibbs, and also between the definitions of grain boundaries and so on and so forth is rather uninteresting. Yeah, so it might be, your interfacial axis might be 5 atoms per square nanometer, and if you move your interface over by 3 nanometers, it might be by 1/10 of an atom per square nanometer different. Yeah, so from an experimental point of view, the difference is not all that significant. Yeah? And of course, this is actually defining the interface based on the concentration. And that's not necessarily always the best way to define an interface, right? We're macroscopists. We might have other ways to define an interface, right? This is pure continuum thermodynamics. Pure continuum thermodynamics, nothing else. Pure continuum thermodynamics, continuum thermodynamics knows nothing about crystal structures. Yeah? It just knows if I have a crystal somewhere, that crystal has some thermodynamic properties, but it knows nothing about a crystal itself. But we know things like that. We know that a grain boundary, for example, is atomically sharp. Yeah? And so we can use additional knowledge to define the interface. But this is just a rundown on why you will see discussions on what is an interfacial access and why, as an atom prober, you usually don't really have to care. Yeah? So especially old people in our field very often will get worked up on that, and then you can ask them if they've tried to determine the difference between the interfacial access in the atom probe data defined after Guggenheim and after Gibbs. And there's certainly there's certainly differences that are larger than the difference in definition. Yeah? But it's true, the Gibson interfacial axis is not a thermodynamic value. Okay, good. So what we're going to do now is we're going to determine the interfacial axis value for the grain boundary that we've looked in earlier, the very simple one. And to that end, I will just load all of that stuff in again, and I will kick out all of the stuff that we did in the last session. So let me just clear all of that out. And I will just load in the POS file that we've used earlier, which is simple grain boundary in simple grain boundary, and it's an EPOS file. Open. Then we need our mass spectrum, so I'm just going to reuse the code here. So we've got our mass spectrum, and then I will allocate the ranges. So we got POS allocate range, and we are going to do it on an atomic basis again and not on an ionic basis. And now the only thing we will need on top of that is our grain boundary that we've created the very nice grain boundary model earlier. So I'm going to go and import the OBJ file where this is saved. Grain boundary 2, open, and let me just plot all of that. So species is born in this case, and let's get up post data. Oh, and we need the color scheme, and we are also going to load the table with the isotopic abundances and plot all of that again. So the question is, do all of you have the grain boundary model so that it can work along? Yeah, okay, that's good. That's good. And I will chuck in that I will chuck the comments into the chat soon. Yeah, so we're gonna hold on, and we are going to OBJ fv dot vertices and fv dot faces, and going to plot that patch. And I will just close all of the other figures. And there we go. We've got a nice grain boundary model and plotted over boron, so that's probably a pretty good starting point. Yeah. And that's all we need. And I will just copy all of that except for the one here. And now all we need to do is go patch create interfacial access, create access value, create access value. The reason why it's not called interfacial access value is because the access value, you know, the concept that I've just introduced, and I'm going to draw that in a second, doesn't just work for planar interfaces, but it also works for points. Yeah, I can create a point axis. You can create a line axis. Yeah, so it actually works independent of the dimensionality. Okay, so what do we need? We need the atoms. We need the boron atoms, or whatever species we want. And we need the interface, and that's actually all there is to it. And what will happen now is we will have a little interface popping up. We'll have a little interface popping up, and that interface is exactly the curve that I've shown you earlier. But obviously on a modern atom probe, if we compare that to what we've seen just before, no, that was I think I did it in Firefox. Of course, if you look at this here, this is a one-dimensional atom probe. Here's the counting statistics. So you can see the cumulative number of atoms here is about, I don't know, 300 for the entire data set of 9,000. Obviously, in a modern atom probe, you get a lot more data than that. So you get 3,000 atoms in 3,000 atoms versus, I don't know, about a couple 100,000 atoms. So, a million atoms. Of course, the data set is a million atoms. And this is a small data set these days. So you can imagine the determination of interfacial access in a modern atom probe data set is a lot easier than it used to be. And here in the interface, we've got a couple of things that we can do. Well, the interface will pop up with actually pretty okay defaults usually. So you can see we have a line here that's denoting the concentration on the left side, and one here that's approximating the concentration on the right side. And what we see is that we have an interfacial access of about 2.5 atoms per square nanometer. Does anyone have an idea of, is it much? Is it not a lot? I don't know. Well, to give context, one monolayer in iron, I know it for iron, I don't know it for nickel, it's probably not going to be much off. For iron, one monolayer of atoms in the most densely packed direction, 110, is 13 atoms per square nanometer. So this would actually be if it's all in one plane. From atom probe data, we have no way of knowing if it's all in one plane. But if it's all in one plane, then it's about a fifth of a monolayer. It's about a fifth of a monolayer. Okay, so but what if this approximation isn't all that great? Well, the one thing we can do in this interface here is we can change the limits. So here we can see also we have partial access. This is something we didn't have before. But in atom probe, because we assume we have some good idea of where the interface is, we can also say, we can also go, if I go back into the sketch here, we can also say, okay, do I have more stuff on this side of the boundary or more stuff on this side of the boundary? Of course, if I use, for example, boron to define the interface, it doesn't make much sense to look whether I have more access on one or the other side. That doesn't make all that much sense. But if I have some other idea of where the interface is, then it can actually make a lot of sense to look at partial accesses. And here we've got a partial access of about 0.9 atoms on one side and 0.61 on the other. And this is mostly caused by the preferential retention in this case. So, but what if these were to be not so great approximation? So here maybe you can see the limit here is already a little bit off. So it's not you can see this is not linear anymore at this point. So what we can do is we can click at change limits and then click nearest to whatever limit we want to change. So here I want to change this limit. And then I click to where I want it to be. So now it's moved over here. And I can do the same thing with this limit. So I can move it over here. Obviously, the axis hasn't changed very much. There was already a pretty robust determination because we have a very clear axis. We have very clear concentrations on either side. By the way, this if you click somewhere near the border, it's just that the second limit of the determination is just at the border. So I can click here and move the second limit here. And now we've got the linear approximation in this area. Again, the change is in the third digit. So yeah, maybe not that relevant. And we can also move that one here. And that's actually all there is to determine an interfacial access using our toolbox. So yeah. Very, very simple. Of course, we want to document everything we've done. So what you can do in this case is click the figure save button. And what that will do is just create a figure, which you can save. You don't need to do that. You can opt to not save it. and we'll just create a figure that just displays everything you have done. And then you can just move stuff around so that it's nothing's in your way. And that's something you can put into your analysis folder. You can go and put into your analysis folder. And you can go up. And this is usually how you should name it. Boron access. Boron access, and I can save that, and then or export it to any format I like. And just use it to document everything. Okay, and then I can just go and close my interfacial access determination again. And now if I open the data set again, then we're in the wrong folder. Simple grain boundary, and here we now have the access figure, and I can open it again, and you can see everything is still here. So have some of you managed to create an interfacial access value along with me? Oh, come on, that should have been easy. One green tick. Two is better than one, twice as good as one, in fact. Okay. So so now we have calculated an interfacial access value for one single interface. Okay, so now let's get into something a little bit more interesting, into some interfacial access mapping, because the interfacial access, that can also change across an interface. And while concentration mapping of an interface can sometimes give you very good hints of where to look for variations in concentration, for the same reasons I've talked about before, it's not that robust a value. Yeah? So very, very often you might want to map the interfacial access rather than you wanting to map the concentration. Yeah? Okay, and so let's get into that. And for that, we're going to take a new data set. And so I'm just going to clear all of that out. And I'm just going to copy that one command in. And now I'm going to load in pause to table. I'm going to load in the nano duplex steel. The nano duplex steel. That's also a fairly large data set. That's a data set that my colleague Saritha Samudrala back in Sydney has acquired a long time ago. What's interesting about the data set is it contains an interface between austenite and ferrite in a duplex steel. It's a nanostructured duplex steel, but that's not that important for this case, but it's a duplex steel. So we have various interfacial accesses, and you'll see that they actually vary across the grain boundary, and so we can do some pretty funky local proxygrams, local interfacial access determination, interfacial access mapping, and so on and so forth. Okay, so let's also load in. Let's load in our color scheme and everything, and load in our range figure. Okay, so we've got our range here. In this case, there's some peaks that look a little bit weird. I don't remember why that was the case. Anyway, doesn't matter now. We're just assuming our atom probe data is perfect as always. I go pause allocate range, and we're going to work with atoms again. So we're going to forget about all those pesky ions that we have. We're just gonna work with atoms. And how many entries does that have? Is that 3 or 30 million? I think, no, it must be 3 million at 30. Yeah, it's, no. Okay, By now my eyesight is declining. Now it's a 31 million atom data set, so it's a fairly large data set. Yeah? So we can work with that pretty well. And if I go right, I've given you the interface. No, that's simple grain boundary. And interfacial axis, nanoduplex steel. Do all of you have the grain boundary for that one? Martina is green. So you should all have a 3D object called whatever grain boundary, and that's actually a fairly good model of that grain boundary. It's a fairly good model of that grain boundary. In this case, because it's actually a phase boundary, you could use an isosurface because there is. Let me show you. Let me just show the carbon in this case. Yeah. So if you look at the carbon, you could use the carbon and create an isosurface. Could create a carbon and use carbon and create an isosurface. Let's just create carbon. Let's just display carbon and boron. So you can see we've got some pretty decent interfacial axis of boron here. It's a little bit distributed, a little bit fuzzy, and we can see maybe there's a little bit of difference between between the local concentrations of boron here on the interface. And let me just export the boron. Pause to OBJ. And we want to export boron in this case as well. Boron's pretty prevalent at the interfaces apparently. So we'll save that out. And let me just get into Blender, and I'm just going to delete all of the objects in there. I'm going to unhide all of them and go and delete them. Then we file import wavefront OBJ and go to the folder, interfacial axis, nanoduplex steel, and there we've got some boron. And in this case, again, we need to keep the vertex order. Y forwards the up, that's still okay. And you can see if we go into orthographic view, it's actually relatively easy to see the grain boundary here. And if you want to see that a little bit clearer, one thing we can do is go into edit mode. Select the object, go into edit mode. Deselect everything, just use circle select, and essentially delete all of the atoms that are definitely not on the grain boundary. Oh, and we need to change the depth buffer. No, not viewport. We need to go into wireframe view. Otherwise, it's depth buffering. You don't have to worry for now what that means. And we can see, okay, there are certain regions like up here where we have more, and here where we've got less, and here we've got a little bit more, here we've got a little bit more. So there's certainly a distribution of boron on that interface. I don't know if that's a precipitate starting or whatever is happening there, but there's certainly a distribution. Certainly some kind of distribution that will be interesting. Of course, we could now go and start modeling our grain boundaries. So, Now that I put a mesh bit in, it started thinking that there should be a mesh, but anyway, that it stopped displaying the vertices. Mesh plane, and now we could go and grab that plane, now put it somewhere, oops, grab that plane, put it somewhere here, scale it up 20 times maybe, then rotate it, rotate it in this direction as well, and so on and so forth, scale it up even further, and go and create our model, create our interface model. But I think in the interest of time, that's really homework for you. You can go and try and outline the interface and make a good grain boundary model from this interface. Okay, but we've loaded it all in, and I think we've loaded it all in already. Have we? No, we haven't. So we need an OBJ. Object is OBJ to patch, and we are gonna grab it from the duplex deal, which is the grain boundary here. Open it up and then define our analysis object. And now we should be able to plotted a lot of stuff. Get rid of that, get rid of that. It's the old mass spectrum. That's the isosurfacing. The app designer we can don't save. Yeah, and here, and I'll just go and plot that patch. And you can see we've got this grain boundary outline, which has been made using all of those funky algorithms that I've showed you earlier. And this is a pretty good model, and you can see it's got a very even distribution of individual vertices that we can actually use to work with. And the very first simple thing we're going to do is just to create the interfacial axis. We can check the same thing as we did before. Just to demonstrate something, I want to show you the carbon interfacial axis. That's why I pulled that up. So, and in this case, I want to have the carbon one, because in carbon we've probably got some excess, but also we've got a different level of carbon on either side of the boundary. And of course, this is a fairly large data set, so it will take a second or two. But you will also see that our interfacial axis calculations in the 21st century, essentially 30 years after the work from Northwestern, of course, our statistics are vastly improved over what we see here. The one thing that's really missing in this case is that I think it would be really nice if MATLAB had a highly parallel sorting algorithm, because most of the time that we have to wait for interfacial axis value is actually it sorting all of the atoms with respect to the interface. And while I was saying that, I could actually think of a way to do that. So I might just implement that. What you can see here is that probably we don't have a lot of interfacial axis really here. So you can see we have two different concentrations on either side, and the interfacial axis nominally is 0.2 atoms per square nanometer. And considering how good the statistics are, that's probably true, and it's definitely not a lot. So if we go and look at boron, I mean, we could do a proxygram and just look up which species are enriched. This is usually the starting point, and then just calculate the interfacial axis for the species that are enriched. because whenever you can calculate a proxygram, you can definitely calculate an interfacial access value. You could even calculate interfacial access values from proxygrams if you knew how many entries, how many atoms contributed to each bin in your proxygram. If you have that information, you can calculate that the other way around as well. But using those cumulative curves, that's a bit more of a robust way to do it. So in a couple of seconds, hopefully this should pop up. So distance sorting algorithms are one of those other things that are extremely impactful. If you come up with a highly sophisticated sorting algorithm, there's always use for that in informatics. Okay, so here we have an interfacial access of about 0.8 atoms per square nanometer. So this is, for example, a lot less than what we had before. It just might look like it's a lot more just because we're looking at a larger interface, but the interfacial access is a lot less than what we've seen before. And again, I can change the interpolation limit here, from here to here, maybe from here to here, and from here to here, but it doesn't have a lot of impact. Okay, so the question is now, how can we do that locally? And we've already seen that with the proximity histograms. But we can do the same thing with interfacial access. But before we do that, we can actually create a map of that, so that we can see where the interfacial access is higher and lower, or where the concentration is higher and lower, so we can get some idea of what stuff looks like locally. And I will just do that creating a 2D concentration map, and P. Sorry for the workaround, we will fix that. And in this case, we are looking at boron. And this time it's a little bit more interesting because we're not looking at an iso-boron interface. So we'll definitely make it so that you can just use the usual ways we do it usually in the toolbox. In this case, I don't know, is 4 nanometer a good measurement? We can have a look. This is 20, yeah, maybe 4 nanometers, 4 or 5 nanometers. Why not? Maybe we'll make it 6. Maybe we'll make it 6. So one question in the chat was sorting. What I mean by sorting. What I mean by sorting is sorting the atoms according to the distance to the interface. Which we don't really need to do when we, for example, create a proxygram, because with a proxygram we only need to say, okay, with if you're closer than this or further than this, you're in that bin, and so we'll take you into account. In this case, we actually need to sort them, and that's you're sorting 31 million atoms, so this takes a couple of seconds. But it's getting faster and faster because these are fairly large data sets, and it didn't take all that long to sort them. So in order to be able to fix the problem here, that you needed to pull out the coordinates from the individual species by hand. Fixing that is actually fairly simple because it's essentially really just those two lines, and we're going to put them into the code. The problem with that right now is, of course, we would have to redistribute the toolbox to you. So that would just hurt us a little bit in our workflow. Yeah, and here we already see, okay, we have local differences in the concentration. And it might look like it's not a big difference, yeah, but we have concentrations of close to 0, yeah, versus concentrations that are 0.8%. Say 10 to the minus 3 means 0.1% is 1 to the 10 to the minus 3 is 0.1%. And yeah, so you can see this is already a Voronoi centroidal Voronoi tessellation best optimized interface, yeah, for a nice curved interface. Yeah. Okay. One thing we can do with that is export it. But we were missing one function in the exporter, which is a bit of a shame. But nonetheless, I'm going to show you what I mean by exporting. So if you look into the folder here, you've got something called a PLY. Yeah? A PLY. And a PLY is also a mesh format. It's a mesh format, but the difference between a PLY and an OBJ is in a PLY, you can have multiple properties. So in this case, we've exported this interfacial axis map, and it will tell you, okay, what is the minimum interfacial axis value, what is the maximum interfacial axis value, and then this is just displayed as a property of the vertices. So you can see here, you've got a list of vertices then, and each one of those vertices has 6 values now. You've got a coordinate x, y, z, and then you've got further values. In this case, these further values are RGB values, are color values. But the PLY format allows you to have more than that. Yeah? So it's a format with a header. Yeah? And in that header, I could add more properties. Yeah? So I could define a property interfacial axis, which I haven't done because I don't know why. I could do that. Yeah? So you could have another column here of interfacial axis. Yeah? And these are per vertex properties. And then you've got faces, and in this case, the faces are also, you can have polygon faces. Yeah? So it says this is a face with 3 vertices, and these are the 3 vertex indices. That's why I always see a 3 here. Difference is, I think, if you want to have multiple objects in there, I don't remember what multiple objects look like in a PLY file. You can look that up in the file definition. Yeah. And you can also have PLY files in a binary format. Yeah? So this is an ASCII format. So it's a text format, but you can also have them in binary formats. And you can go and import a PLY also in pretty much any 3D program. So Stanford PLY format. And let's go to the nano duplex deal where we've got the PLY, and you can import it. And why did it not pop up? Did I do something wrong? Import Stanford polygon format. That should actually work. That's a demonstration effect. I have no idea why it doesn't import the PLY format, because when you import a PLY format, it will also import the properties, the mesh properties you import, and it will know that it has vertex coloring. Yeah? So you will have those colors that you've allocated in MATLAB. You can also access them in Blender and essentially say, okay, give that color to my object. Yeah? And this is great for visualization, of course. Okay, but I've got to check on why this is not working. But anyway, the point is you've got color information in there. Yeah, so you've got color information in there, and here we've got the concentration information. And so without exporting the PLY, obviously it's a bit hard to know where you would do your local interfacial axis calculation. But I'll just assume that somewhere in the middle here we're going to have less, and somewhere here at the top corner we're going to have more. And that's just something I'm going to mark in Blender. So I'm going to go File, Import Wavefront OBJ, and we're going to import the grain boundary. So we've got our grain boundary imported. In this case, I don't think it's that bad because we can actually see where we have more boron. So I'll just click on the filtered grain boundary, go into edit mode. Am I in edit mode? I am in edit mode. Oh, there's a bunch of other things that I've done here, so don't worry about that. And what I'm going to do is I'm going to compare the interfacial axis up here, which I'm going to allocate to a vertex group called, I don't know, maybe I'll call it top, even though here in this display it's bottom, but Adam probably wise it's top. And assign, Alt A to deselect, and then maybe we'll select this area here. We'll select this area here, create a new vertex group for it, call it mid, and assign. And now if I deselect, if I move here and go select, yeah, that's fine. And check here the selection, so that's also fine. And then I can go and export that again. So I'll just go out of the editor, go File, Export Wavefront OBJ, and now we'll call that something completely different because we're gonna go here, grain boundary 2, V groups. So we've got the vertex groups in there, and we'll just make sure that we have the poly group selected and export all of that and pull that back into MATLAB. Including the groups. On a duplex deal, here we have it with the vertex groups. We can pull that in. And then we've got our initial structure with group, and where we can see which vertices belong to the individual groups. And unfortunately, we're going to have to use the same workaround as before. Again, we're going to take care that this is going to be included. Oh no, for the interfacial axis, I've implemented that, so don't worry about it. Sorry, I was talking, and I probably should give you all of the various commands. Okay, so apparently there has been some changes with the definitions of the PLY files with Blender. I have to check on that. PLY files were actually just like OBJ meant for eternity. So So I have no idea why they've changed something around that, but I will definitely check up on that. The thing is, in recent years, I usually for publications I just used MATLAB and just used the MATLAB figures and didn't bother going to Blender. So I didn't use the PLYs all that much anymore. So, but I've got to check up on that again. Okay, so that's copied in, and now we can go batch create access value, and here we should be able to go group one dot vertices, group one dot vertices, and we should actually be able to do the same thing with the proxygrams. Sorry about that. And we will definitely implement that very, very quickly. because local proxygrams are extremely useful. Okay, so this is our first interfacial access value. So this is now for the first group. We can go into the group variable and look up which one's the first one. The mid one, so the lower one, with less interfacial access, or apparently less interfacial access. And now we'll just calculate it for the second group of vertices, which are the top ones. And we're also going to throw in a function that it just allows you to pull out the subvolume that's associated with your local value, so that you can use all of the other funky stuff that I've showed you earlier with chopping up your data set and things like that. Or for example, creating a domain for analysis objects to say you've got a precipitate sitting somewhere and you only want to have the atoms that are really associated with that precipitate. It's the same thing. You can just say, give me all of the individual give me all of the individual precipitates here. So what we can see here now is that we have just shown. It was supposed to open. I've never had that issue before. I hope that's not a Windows versus Mac thing. I mean, for demonstration purposes, it's now cool to see that the interfacial access is really higher on the second calculation than on the first one. But that was maybe not that helpful. Anyway, so let's recalculate that. Was a bit stupid. Okay, let's just create the axis figure for that one. So here we've got about 1 atom per square nanometer. And let's calculate it again for the first one. And again, it works for an isosurface just as well as for some grain boundary that's been modeled with a lot of lava. did it? That is weird. I really have to check on what the what in God's good name is going on here. Anyway, so here we've got 0.6 atoms per square nanometer, and on the early one we had about 1 atom per square nanometer. Maybe we'll just redo the interface here to bring it into the 21st century, because this is a little bit. I mean, it's fully functioning, you know, no errors or anything, but this was some this could be a little bit prettier. Okay, so we can now calculate interfacial access, and we can calculate local interfacial access. So the last question we have is, can we do interfacial access mapping? So can we make a map of the interfacial access? And that's also something we have here, which is called patch create interfacial access map. And this one, I really hope it's been brought into the 21st century as well. Otherwise, we'll. Oh no, it says needs rework and documentation. That's always great if you read that. Anyway, what we need is we need our POS, we need our interface, we need a limit, and we need something called delocalization, which I'll get to in a second. So we'll go IE map. Okay, we apparently haven't used it recently. So we need our POS, which I assume is not in the form of a table, but we'll find that out in a second. We need our interface, which is our FV. So interface, we need a limit. Again, this is now Guggenheim definition. So our limit will be 4 nanometers. And we need to have a delocalization, which is just taking care if we have noise in the measurement data. And I'll explain all of that in a second. Yep, so sorry, there needs to be some recoding. So what we need is, no. Same as before. So we're just taking the atomic position of boron in this case. And okay, I should have tested it a little bit better. So we are missing a, so if I set it to 0, then it should work out. Sorry, we're missing a function here. Duplex steel, IE map. _2. And there is no function called patch2ply, because that's called patch2ply, and that function was missing something. Okay, maybe that wasn't as tested as thoroughly as it should have been. I apologize for that. Save the changes. If we don't save the PLY, we get no problem with the PLY saving, so we'll just do that. And what we get here now is a map of the interfacial access of our grain boundary here. And one thing we can do is edit the color map. Because right now I think some of the differences are a little bit harder to see because of the color map that we're using. where you can see you have areas with higher interfacial axis and areas with lower interfacial axis, but you can also see that the statistics that we have are somewhat limited. Yeah, and that's what I said earlier. You know, if you have a little bit of a coarser mesh, then you would have more data per vertex that you can work on, and then the whole thing would look a little bit less noisy. But you can still tell, you know, we've got more interfacial axis here, and we've got less interfacial axis here in the middle, which is also something we could confirm by just putting our interfacial axis measurements there. Okay, so a little bit of an explanation of what was happening here. So essentially, the interfacial axis measurement that we did here was the Guggenheim interfacial axis measurement. Just simply because it's a little bit more robust. Yeah, if you have got a lot more data, then you can also do the whole thing with the cumulative curves. But that hasn't been migrated at all yet, so we might migrate it in, but that was a bit beyond what we wanted to do today anyway. So let me just quickly show you what we've done here. So let's go to the tablet. So what we've done here was very simple. So we have our interface. Yeah, so we have our interface. And we've defined with those 4 nanometers what our interface is. I should have maybe made it a little bit thicker than that. Maybe I'll make it 8 nanometers. We get a bit better statistics. Okay, so we've got our interface. So essentially the whole limit of this being x nanometers thick. And then we have our boron atoms that sit around here. And then you have some boron atoms that are away from the surface. Yeah? And what we have done is essentially we have calculated a background concentration. Yeah? So we've looked at how many atoms do we have here compared to here. Yeah? So we've created a Z0. Yeah? So if you remember the cumulative curve from before, then we used to have something that looked a little bit like and essentially this slope here, this is Z0. And what we have done is we have wrapped that thing around itself, and we've determined one Z0 for the data set. Yeah? It's a bit of a limitation of that algorithm, but I haven't moved the full powered algorithm that does like a cumulative curve for each one of the vertices into the new toolbox yet. But I guess I'm going to do that pretty soon as well. And what we've done then is the Voronoi decomposition, just like we've mentioned before. So we've subdivided that here and just calculated how many atoms do we have in each box. In this case, it would be 5 atoms. In this case, it would be 4 atoms. And in this case, it would be 1, 2, 3, 4, 5, 6 atoms, and so on and so forth. We've calculated that, and then subtracted from those atoms. We have the concentration C0. So the amount of atoms. So we have calculated the amount of atoms per cubic nanometer outside of our domain here. And that is the C0. And subtracted that from the number of atoms inside our boundary domain. So this is the simplest way of determining an interfacial axis. but the good thing about it is it's relatively robust, even if you have not that many atoms at the grain boundary. Yeah? And if you think about it, if you make the small boxes around here at the interface, probably you really won't have much more than a handful of atoms associated with each vertex. If you have a thicker um, boundary with a lot of stuff added, then of course you can go up to the next level of interfacial access determination. And just to give you a heads up of what that looks like, that looks a little bit different. And the way that looks is we're doing it without partial interfacial access. So what you're going to get is the sum of species I, with respect to the to atom I, and this is sorted by the absolute of the distance d to the interface, and not by the value, but by the absolute value. And the reason for that is then the whole fitting process becomes a lot simpler, because what you're going to get is a curve that looks like this. So it's essentially this curve at the interface here wrapped around itself once. And the good thing then is that you only need one linear interpolation. Sorry, that was not a particularly good one. So you need one linear interpolation, and you get your interfacial access count at the interface. No partial accesses, but just the absolute access count. And I'm sorry I haven't pushed that into the toolbox yet, but that's something that certainly can be done relatively quickly. Okay, so with that, I think we're moving towards the end of the winter school. So do you have any questions about interfacial access and interfacial access mapping? So I surely hope that a lot of you are using interfacial access calculations if you work at interfaces, because as I've mentioned a couple of times, it's just a lot more robust than doing simple concentration calculations. And if you have a model of your interface anyway, it doesn't matter if you have an isosurface. If you were able to create a proxygram, you're able to create an interfacial access value. And I would really, really appreciate if all of you, if you write papers, if you include interfacial access values. It doesn't matter if you use our code here or if you use someone else's code, but please include interfacial access values, because they are a real robust measurement of the amount of segregation that you have in equilibrium. Of course, if you've got an interface with a concentration profile that looks like this, of course you need to make sure that you're only looking at the interface. You're only looking at the interfacial axis in sort of this area, because the outside is obviously some diffusion still going on. In this case, obviously, then the interfacial axis is also not a thermodynamic value. In this case, obviously, the interfacial axis is a measurement of the segregation at that moment, because there must be some diffusion going on. Okay, and with that, I would like to thank everyone that was part of the of our Atom Probe Winter School this year. It was 3 days of me talking a lot, but I hope some of you at least have taken some valuable information home, and will be able to do a bit of an improved analysis on your own data. So with that, do you have any questions that are left? Not necessarily just about interfacial access, but maybe about anything related to our Atom Probe topics that we were talking about. Martin, you have questions?
Not really. I just thought that it might be also time for me to say a few words, but I think we just wait first for the
I'm gonna be online for a couple more minutes anyway afterwards if you've got questions. So Martin, just shoot away.
Yeah, so also from my side, I'm quite happy that there are still lots of names online. I hope that also the faces are sitting in front of the screen, or at least the interest is not in the weekend already. Yeah, I'm kind of still also happy if there is feedback or some questions about the troubleshooting, so you can still continue to write, especially me. And if I don't have time to answer questions, I might just distribute it to Martina or Bene. I think there were not that many questions yet, but maybe if you start doing
There are some questions that came in the chat directly to me. The first one is when can we expect the YouTube videos to go up? Well, all of them are already up except for the one that's currently recording. Yeah, so the other ones are already up on my channel. And what is the frequency of toolbox updates? Yeah. So if you have anything with the toolbox that's going wrong, just shoot us an email. Yeah. We will set up a bug tracker on Git, so that we can track the bugs, and also a version registry. Now we haven't had versions up to now, but I think now we're going to do versions so that you can always say, okay, I was working with version 1.05 or whatever, and we can find any problems if there are problems. And of course, if you have set an analysis setup and we change some functionality, that you can still use the old functionality. And the frequency is, if it's smaller things, like all of the issues that I ran into today, they are relatively small things. Yeah, they are things that I can fix in probably an hour. All of it together in an hour. Yeah? So this is not a lot of work. So we're going to put that up relatively quickly. And with the versions, if you download the programs fresh from GitHub, then you will always have all of this stuff there freshly. All of the stuff there freshly. And with the toolbox versions, it's a good question. How often should we do versions? Probably every time we have one of our workshops, one of our schools, which will be once a semester, because it's also now part of a module here in the material science studies in Erlangen. So we are kind of forced to offer it once a semester. And I would think that we are gonna make a release every time before that. So every half a year, unless there is a good reason to do it in between, then we'll do a release in between. But you will always get the latest if you just download the latest version from GitHub, because that's where we're actively developing. If you want to contribute, if you have changed something or come up with something that's really cool, that works with our toolbox, we're happy to integrate it as well.
Maybe also just a little comment. Things Peter discussed at the beginning, which are not implemented, might have been already done, but are just not part of the toolbox. For example, the sexy plots, or the not sexy plots, the correlative fit plots. There is a fairly good working routine around, and if there are people who really need some opportunity to plot it, I think just shoot an email, and we would be happy to discuss what exactly is needed, and then maybe also migrate it part of us. So there's certainly just lots of work to be done for sure, but yeah, I think we are in for the competition, so we are trying.
Yeah. So the difference between the Atom Probe toolbox and the other code that we had is the Atom Probe toolbox is really based on the concept of tables in MATLAB. Yeah? And you've seen a lot of tables, for example, the pos variables as tables, and so on and so forth. And this is why there were some things that didn't quite work out, because before we just had arrays. A pos variable was just an array, and you just had to know which entry is which. Which becomes problematic once you start tagging your own analysis on top of the data that's already there. Yeah. For example, if you have an entire column there denoting to which subvolume which atom belongs. Yeah. And then the length of your array changes and so on and so forth. And you can do that very easily with tables. Yeah. You can just add another column in the table that just denotes something about your atom. And this has been going on here now for about 2 years. But before that, all of the atom probe code that I had was in this other repository, which is also public, which is called atom probe code. Yeah, and there's a lot of stuff that's in this atom probe code that we haven't quite migrated yet. There's a lot of stuff in there. It's also not as well documented. So, for example, if we go into pseudo 2D concentration map, there's a little bit of documentation, but not as much. Whereas with the atom probe toolbox, unfortunately, you've seen some not so good examples as well. But usually, if you go into any function here, everything is very well documented. You know how to use it. It tells you what it does, what comes out, gives you useful notes, and so on and so forth. And that's a little bit of work. And I'm trying to get students, not necessarily my PhD students, but other students to help with migrating and stuff like that. But getting material scientists to code is sometimes a little bit hard, unfortunately. Yeah, but we're doing our best to migrate everything that we have into the toolbox, and maybe also to get some external stuff to go into the toolbox. For example, the guys in Norway have done a lot of cool stuff with their user interface based MATLAB analysis thingy, and they have implemented some of our codes in there, and maybe we can implement some of their codes in our much more scripting based approach, because our approach is meant to really power automation. So you have 100 data sets, just let it rip through 100 data sets. But they have interesting things like spatial distribution maps, for example. Other things that haven't been migrated is some of the cluster analysis. There was also a question that came in the chat right now. Can we do cluster analysis? Yeah, we have some pretty good cluster analysis code, also based on Voronoi diagrams. You see, I love Voronoi diagrams. But that's not been migrated. You will find that in the atom probe code folder. There is cluster analysis. Oh no, this is not. This is a tutorial I gave. But there is cluster analysis in there. Clustering wizard, cluster type animation and stuff like that.
Peter, I think it's already in the toolbox because I already used it and I changed the code.
Okay, then it's in the toolbox already. So we have a self-consistent approach to clustering. Clustering is kind of like histograms. There is no one way to do it, unfortunately, no optimal way to do it. But we have, I've programmed one ages ago that is self-consistent at least, so you don't have to do anything. You can just press go, and it does its thing. But yeah, thanks, Martina. So apparently that's already in the toolbox. So that's all good. It's probably, that's the atom probe code. All right. But if you have any trouble using the toolbox, just shoot us an email. Very often it doesn't take that long for us to find out what the issue is, and if it's a bug, we can fix the bug. All right, and with that, I would like to thank everyone. Should we do a group photo? A Zoom group photo? Yes, no? Martin says no. Martin didn't shave this morning. I didn't either. All right, we'll let you off the hook this time, but next time you can come to Erlangen, and if you're in Erlangen, we're definitely going to do a group photo. And I really hope the next school can happen in Erlangen in person, because we have got a lot of really cool stuff for an in-person school. So we got an old atom probe detector from our friends in Leoben that we're gonna plonk onto our FIM, so you can go and play with an atom probe detector and oscilloscope. We've inherited some pulsars, so we can do some pretty cool stuff in playing around with atom probe tomography, and then you can do reconstruction on atom probe data that you've created by hand. All 20 atoms that you've created, all 20 atoms that you've collected, you can create. You can reconstruct by hand. So yeah, let's do a group photo. So I'll stop the screen sharing. I'll stop the screen sharing. And I I guess in this case nobody can see me, right?
No.
Yeah, that's because with OBS open, unfortunately the camera has been grabbed by OBJ by OBS, not OBJ. But of course, if you're sitting at home and you've been watching us while sitting in the bathtub, yeah, we're not gonna force you to switch on your camera. I'll just Photoshop myself in later. Okay, and there's a couple of people we lost. Martin, can you do the screenshot, because I honestly don't know how to do that on Windows.
I'm searching for this too because I'm on the surface right now. Maybe
It's just snipping tool.
Okay, Martina, you do it.
Okay, everybody please smile. I have one, thank you.
All right, that's great.
Thank you.
All right, so yeah, thanks to everyone, and I'm going to put on the last video onto YouTube straight after the session, and then everything can be revisited on the on my YouTube channel. All right, have a nice weekend.